I've had a little bit of a problem interfacing the multiplexer with the coils in order to drive the LED segments. I think this is probably down to the fact that I don't have a negative power line for the sinusoidal input, and I could add one, but I thought it would be more fun to do it a different way. And my solution for this is this. I'm going to use the output of the multiplexer to drive these relays. Each relay will be responsible for a particular digit. That is one of the 16 wires going through the 7 coils. So instead of the signal going from the multiplexer to the coil directly, what will happen is the multiplexer signal will trigger a relay, and then the relay will switch the sinusoidal signal into the coils for the comparator to pick it up. I think this might end up being quite a lot of wires. We've got the multiplexer sequencing through the relays, and we can hear them clicking, obviously, and the lights coming on, which is grand. This is a little bit fast, so I'm going to slow down the clock a little bit, and that's a bit better, though I'm probably going to slow it down a little bit more so we've got a bit more time between clicks to see what's going on. I've turned the board around so that we can see the 7 segment display up the correct way, and I've turned the power on, and we can see that it's sequencing through. However, it's not necessarily displaying the correct numbers. This is almost certainly a wiring fault. I'm just going to have a quick look and see. Yeah, so that problem was me misaligning pins on the breadboard. Specifically, the ground signal on the coil side wasn't actually connected to ground, and so it was floating on one half of the numerical signal wires, and that meant they were floating, and that meant that they weren't doing what they were supposed to be doing. As we can see here, that is now fixed, although we do still have a couple of wires that are out of order, and I have one number which is not lighting up at all, which is probably again a bad connection. The bad connection was in fact a wire here which had broken off, and I just couldn't see it broken off. Plugged it back in again, and now I have a appropriate character, which is a C. I know it looks like an E, but it's a C. So I'm contemplating the fact that the number 2 and the number 0 are the wrong way round, and if I stop it on number 2 like so, I can now just swap the wires around on the breadboard, which will correct the problem. I don't know where I've got the wires the wrong way around, but just swapping them on the breadboard where they go into the coils will cure this problem. And there we go. We can see now we're going in the correct order for the counting. Excellent. So we're almost finished. I think we're going to zoom in so that we can see it clearly, and I'm going to spend a little bit of time trying to figure out why the G segment is a slightly more illuminated, especially why it's illuminated when there shouldn't be a signal on it. I've replaced just about every component involved in lighting up that center segment. I've changed which comparator it was using. I've swapped some comparators over. I've changed the resistors and the capacitors that are used in the circuit into the digital side of things, and it's still doing it, although it's a little bit less than it was, partly because I've turned down the exposure in the camera. The only conclusion I can come to is it's the actual coil that's got the wires passing through that's doing something a little bit different to the other coils. I'm not going to mess about with that. I'm just going to sit here and watch it count, and we'll just have to accept the fact that that middle one at the moment is a bit annoying. You can see from the wider view that it's, the project is taking up quite a bit of space on the desk, and actually it goes off the top of the screen here as well. So I thought it'd be an idea just to give you an outline of how it all works, because I'm aware that it's been quite bitty, which indeed it has been. So if I bring up the block diagram of the circuit, we can see that it basically consists of 4 parts. The bottommost part is the counter, and this takes a square wave input. I think it's taking about 3 kilohertz or something like that, and that is then divided in the divider down into 4 signals, and that's using a 4020. Those 4 signals are then fed into the multiplexer, and the multiplexer then selects one of 16 lines based on the 4 signals, the 4 binary signals. Now, if I wanted to select a number directly rather than having the circuit count, I could disconnect the divider and just put the binary coded hexadecimal value that I want into those 4 inputs on the MUX. The output of the MUX then goes into the relay board, which is an addition that I wasn't expecting to have to put in, but have put in. So if I bring up the schematic of the counter, we can see it here in all its glory with the relays. If I zoom in at the top here, we can see that there is the divider circuit there, and it takes an input pulse. It's coming from the signal generator, and that input pulse then feeds into the clock, which is around here, and then the 4 outputs come down here, and I've picked those outputs because they're the slowest and it divides it the most, and that's purely arbitrary on my part. I could have picked higher ones and just turned the frequency down. It doesn't actually matter. The outputs of that then go into the multiplexer, which we can see here. On the input of the multiplexer, we can see that here are the 4 binary coded hexadecimal signals, and that's just coming out of the counter. And then we have the common, which is actually the signal that's fed to the outputs, and that is just connected to ground. And the reason for this is because the relays are active low. If the relays were active high, I would put it up to VCC up here. On the diagram, the outputs are just onto these labels here, and these labels come down to the respective relays. If the output is selected on the MUX, then the relay in question signal is taken low, and that activates the relay. Now, the relays on the board they have optical isolators and some buffers in between them and the signal. For the purposes of simplicity, I'm just showing it as activating the relay directly. On the common of the relay is a sinusoidal signal. That's hard to say when you've had a drink. A sinusoidal signal which is fed into the common of the relay. When the relay is not active, i.e. this is not low, the signal is fed through the normally closed contact here round to the next relay, and this provides a kind of interlock so that only one of the relays can actually output a signal at one time. It's completely unnecessary, but it makes me happy to have that fail-safe, and it prevents more than one number from being activated through the coils at any one time. If the input signal is low, then the contact flips over to the normally open contact, and then we get an output signal, and that output signal comes through to this magnificent piece of artistry. It goes through the 7 coils, or it goes through some of the 7 coils, and we can see here that I've indicated which coils they go through by a blob to say that it goes through it, and a cross to say that it doesn't go through it. So in this case, relay number 1, or relay number 0 as it's called in the diagram, comes along here, and the cable goes through this coil, this coil, this coil, this coil, this coil, and this coil. And those are the segments that need to be illuminated when you want a 0 on the display. On the other side of the coil network, we can see here we've just got a bunch of resistors and going to the signal ground. Now the signal ground is here and connected to the signal generator, obviously, and that whole signal portion is isolated from the rest of the power and the rest of the circuit. All it does is it goes through the relays and through the matrix we've got here and back down to ground through these resistors, and these resistors purely exist just to not to short out the signal generator. And we repeat that for each of the 16 numbers 0 through to F. So let's pick F just to demonstrate. So F, the signal comes in on the common, the sinusoidal wave comes in on the common via all the other normally closed contacts. So if any of the other previous relays are active, there won't be a sinusoidal signal here. But let's say they're not and only F is being activated. This contact jumps over to the normally open, and then we follow it up, and the bottom one is F, and we can see that A should be illuminated, B, C and D should not be, E, F and G should be. And if you want to draw that out, you will see that that's the actual correct output. So that's how the relay and counter circuit works. If we flip back to the block diagram, we can then see the next section is the coil comparators part of the circuit. Each of these 16 wires go through the coils depending on which of the segments are required to light up. If the wire has a signal through it, then that signal is picked up by the coil comparators and amplified into a 1 or a 0, which is then passed on to the 7-segment driver. So if we have a look at the coil comparators we can see that we've basically got 7 circuits that are the same. Don't worry about this one. This is clock. This is a clock which I'm not using at the moment. So each segment is the same circuit. And if I zoom in on one, say this one, so this is connected to the sense wire of the coil, and the sense wire of the coil just feeds straight into the operational amplifier comparator thing. We then have a couple of voltage dividers just to keep it in the centre, and a feedback resistor, and then we have an output. Then we have an output pull-up resistor, and the output goes out. It's a very, very simple circuit, taken directly from the application notes for the LM393, and it works beautifully, I have to say. And there's just 7 of those. Each of those gives an output for each of the segments, and each segment will get a signal depending on whether or not the wire is fed through the centre of the coil or not. So the next part of the diagram, if we go over to the block diagram again, we can see that the 7 segment driver is the next section. So if we pull that one up, we can have a look. And this one is fairly straightforward as well. So the inputs from the coils come in through here, and there's 7 of them. There's some resistors and capacitors here just to pull the signal down to ground if there's nothing on it, essentially. The values of the resistors and capacitors don't really matter. And then we invert the signal. That's because the comparator is outputting a high signal, that's 5 volts in this case, if it detects something on the coil. However, the 7 segment display is a common anode, which means we have to invert the signal to get the light to come on. And we do that through an inverter, and then the inverter just goes through a load resistor, essentially. In this case I'm using a resistor pack, and then to the 7 segment display. And that's the same for all 7 of the segments coming in from the comparators. The only other connection is the decimal point, which is driven by one of the signals from the counter, essentially, so that I can see that the counter is doing something, basically, and that's it, and that's what the circuit does. The most interesting aspect of it, of course, is the coils. The coils are quite remarkable. It's a hand wound coil. I've wound them myself. The coil itself is a ferrite core, and the wire wrapped around it is just enamelled copper wire. And the way it works, and honestly this amazes me even today, is if a wire is going through it and a signal, an alternating current signal is passed through this wire, that signal induces a current in the enamel wire here, and the enamel wire is then connected to the comparator, which goes, oh, there's a signal there. Now the amazing bit for me is if you pass a cable past it, like so, rather than through it, and you pass that same alternating current through this wire now, it doesn't generate the signal in the enamelled wire. And I just find that amazing.
全然時々